Welcome to Beyond Earth Stories. Tonight, we slip into a journey you don't need luggage for, no hiking boots, no boarding pass, just your imagination and a spark of curiosity. Take a look around you right now. Maybe you're curled up in bed, that faint blue glow from your screen painting the ceiling above. Or maybe you're stretched out on the couch, the hum of a fan filling the room like a quiet lullaby. Now, picture this beneath your feet. There isn't carpet or wood or tile, but a vast sea of molten lava bubbling, glowing, and spitting sparks into a heavy sky. That was Earth newly born, blazing and wild, not the gentle blue marble you know. And honestly, if you set foot there, you wouldn't last more than a blink. Your shoes would melt before you even knew it. So before you settle in too much, take a moment to like the video and subscribe, but only if you truly enjoy what I do here. And tell me in the comments where you're listening from and what time it is for you right now. I always imagine hundreds, maybe thousands of people tuning in from different time zones, some sipping morning coffee, some stuck in the middle of a lazy afternoon, and others drifting toward midnight. Now turn off the lights, maybe let that fan hum in the background, and let's begin our journey tonight. When I say Earth was born, I don't mean it like a poetic birth. It wasn't a glowing orb floating gently in space. No, it was more like a demolition derby of cosmic proportions. About 4.5 billion years ago, a swirling disk of dust and gas around the young sun started clumping together. Picture a construction site where every brick is an asteroid and every spark of welding is a violent collision. Protoplanets slammed together, shattered apart, and merged again, until finally, one of those collisions gave us a ball of rock and fire we call Earth. Back then, the surface was like a frying pan, set to maximum heat, an endless ocean of magma. No oceans, no clouds, no sky as you know it. Just choking gases, dust, and endless energy. There's still a very public academic debate about whether water could have existed in those first moments. Some scientists argue every drop would have boiled away instantly. Others believe that water clung stubbornly inside minerals locked deep within the rocks. Personally, I like to imagine tiny pockets of vapor, like patient passengers waiting for a ride that wouldn't arrive for millions of years. Even in that furnace, Earth was organizing itself. Heavy metals like iron sank downward to form the core, while lighter silicates floated upward to become crust. That dance didn't just shape the layers, it also jump-started a kind of natural dynamo. Our planet's spinning molten heart began generating a magnetic field. It sounds like a nerdy footnote, but it's one of the quirks that saved us. Without that shield, the solar wind would have stripped Earth bare long ago, leaving us as dry as Mars. Imagine the sky above you, not a calm, deep blue, but a choking veil of ash and sulfur gases. Sunlight barely filtered through, staining the air with an amber haze. And every now and then, a meteorite the size of a mountain would slam down, splashing magma like a cosmic fireworks show. If Earth's early days were a rock concert, then this was the loudest pyrotechnic display in the universe. It's funny, really. Today we sip our tea and complain about the weather. But our world once roared like an endless drum solo. In the middle of all that chaos, one quiet force never stopped working: gravity. It pulled in dust grain by grain, pebble by pebble, refusing to give up. If you've ever stuffed all your junk into a closet just to clear the living room, you've recreated the same vibe, messy but effective. Gravity didn't just sweep the floor, it built planets. That's why instead of endless debris fields, we have worlds with names, histories, and moons. And here's something people often get wrong. The beginning of Earth wasn't the beginning of life. Far from it. Life wouldn't even whisper until much later. This was only the opening act, the raw stage setting before the main event. A stage of firestone and unimaginable noise. But in that fury, the foundations for everything to come were laid. Think about this. If you close your eyes and erase your city, your house, the entire world around you, what's left? Picture yourself standing on a balcony above a sea of lava under a sky so heavy with DE dust you can't tell where space ends and atmosphere begins. The ground shakes with every impact, and rivers of molten rock hiss in the distance. From this madness will one day rise mountains, oceans, and yes, even you. That's the paradox of the cosmos. Chaos breeds order. So here we stand at the first heartbeat of our planet. A place utterly hostile, yet secretly nurturing the ingredients for the oceans and skies to come. And in that molten cradle, the seeds of tomorrow were already stirring, waiting for the story of water, our story, to begin. The moon didn't arrive politely. It was born in violence. Picture a cosmic collision so massive, it makes every explosion you've ever seen in a movie look like a sparkler at a birthday party. Sometime after Earth first took shape, a Mars-sized body, scientists call it Theia, smashed into our molten planet. The sheer force of the impact blasted molten rock and vapor high into space, creating a ring of debris that circled Earth like a glowing halo. Over time, those fragments clumped together, cooled, and formed the moon. I find it almost poetic. Something so serene, the moonlight we fall asleep under, was born in an act of raw chaos. And here's the quirky fact of the night: without the moon, Earth might never have become stable enough for life. Its gravitational tug steadied our planet's wobble, making seasons predictable and tides reliable. It's ironic, isn't it? A crash that nearly destroyed us became the reason life could one day exist here. Now imagine what that impact looked like if you were watching from a safe distance, say drifting in some cosmic lounge chair just beyond the blast zone. You'd see molten rivers thrown into orbit, glowing arcs of rock painting across the blackness, like fireworks looping in slow motion. The Earth itself shuddered, its crust torn apart, reshaped like clay under a hammer. The heat was so intense, it could have vaporized any early water, boiling it into space in seconds. There's an ongoing academic debate about just how much of Earth's original water survived that cataclysm. Some researchers argue almost everything was lost, while others suggest the mantle deep beneath the surface held onto water, locked in minerals that didn't care how violent the surface became. Personally, I like to imagine those hidden reservoirs acting like a secret stash, waiting to be revealed millions of years later. And while Earth was reeling from the collision, the newborn moon began its quiet duty, tugging at the tides that didn't even exist yet. Later, when the first true oceans appeared, this gravitational dance would sculpt coastlines, stir nutrients, and write the rhythm of life. Even now, when you stand at the edge of the sea and watch the waves roll in, you're watching the echo of that ancient crash. Let me make a little modern joke to keep you awake. If Earth had a dating profile back then, the bio might have read, recently out of a destructive relationship, still glowing hot, raising a moon together. Not exactly swipe right material, but think about this. Without that event, nights on Earth would be pitch black. No tides to stir the seas, no gentle light to guide nocturnal creatures or inspire human poets. Every lullaby sung under moonlight, every tide pool where life might have crawled forward, every lover's walk on a silver beach, all of it comes back to that one violent impact. And here's a weird side note. The moon is slowly drifting away from us about 1.5 inches a year. That doesn't sound like much, but give it a few 100 million years, and Earth's nights will look different. Tides will weaken, days will stretch longer. We live in a fleeting sweet spot where the moon is close enough to balance Earth, but far enough to give us stable days. Kind of makes you appreciate tonight's moonrise a little more, doesn't it? So here we are, Earth-scarred moon, shining the first hints of stability, settling in. A partnership born in violence, destined to shape the story of water and life itself. But the skies above remained hostile, thick, toxic, and restless, waiting for the next act of transformation. The skies of early Earth were nothing like the skies we know today. Forget blue horizons, puffy white clouds, or starlit nights. Instead, imagine a ceiling of smoke and poison gases, heavy and suffocating with light from the young sun struggling to break through. The atmosphere was thick with carbon dioxide, methane, sulfur, dioxide, and clouds of ash churned up by a surface that never stopped boiling. To step outside in that world would have been instant death. Not that there was anyone to step outside unless you count the rocks themselves. If you could hover above the surface safely, it would have felt like looking into a furnace. The planet was still bleeding heat from its violent birth and from constant bombardment by space debris. Volcanoes erupted endlessly, hurling fountains of lava into the air. The ground cracked and hissed like a skillet left too long on the stove. And above it all hung this noxious haze, glowing orange and red when sunlight struck it at an angle. The sky wasn't just a background. It was a participant in the chaos, wrapping the planet in a cloak of fire and smoke. Scientists sometimes argue about how dense that early atmosphere truly was. Some claim it was so heavy it could crush any delicate structures. Others believe it was more like a thick blanket, protective in its own strange way. That's the fun part of ancient Earth studies. We're piecing together a puzzle with missing pieces, and everyone gets to speculate a little. What's clear, though, is that without oxygen, this world was utterly alien. If you somehow dropped a plant into that air, it wouldn't even get the chance to wilt. It would burn. Here's a quirky little aside. The sun itself was fainter then, only about 70% as bright as it is now. This is known as the faint young sun paradox. With weaker sunlight and an atmosphere dominated by greenhouse gases, Earth should have frozen solid. But instead, it stayed hot, steaming like a giant pressure cooker. The paradox still puzzles researchers today, though greenhouse gases likely played the starring role in keeping the planet warm. Imagine Earth as a teenager, wearing too many hoodies in the middle of summer, sweaty, unstable, but somehow surviving. And it wasn't just gases. The skies were alive with falling rock. Space was still crowded, and Earth's gravity acted like a vacuum cleaner pulling in debris from the solar system. Some impacts were small, leaving only glowing scars, but others were cataclysmic enough to vaporize oceans that didn't even exist yet. The sky wasn't just hostile, it was weaponized. A constant barrage, a reminder that Earth was still being built by fire and fury. Now let me pause for a playful modern joke. If early Earth had weather forecasts, they would have gone something like this. Today, volcanic ash with a chance of meteor showers. Extended outlook acid rain magma, floods and darkness at noon. Sunscreen rating irrelevant. Yeah, no vacation packages were being sold for this place. Still buried in that chaos were the first hints of balance. The heavy gases in the atmosphere trapped heat, while constant eruptions released steam and other volatiles. Over millions of years, these volcanic exhalations began filling the sky with water vapor. Imagine massive plumes rising like endless smokestacks, darkening the air, thickening the haze, and slowly loading the atmosphere with the seeds of future rain. The skies were preparing for an event that would change the face of Earth forever, the first rainfall. But we aren't there yet. For now, it's worth staying in this moment. A world without oceans, without breathable air, without light as we know it. The air was thick, choking, tinged with the smell of burning stone and sulfur. The ground trembled constantly. Meteors painted streaks of fire overhead. And through it all, Earth turned steadily on its axis, waiting. This is the part of the story I find most humbling. Because when we look up at our own sky, clear blue, calming it's hard to imagine it ever being otherwise. Yet, the same atmosphere we breathe today once suffocated the planet, once glowed like the inside of a forge. It's a reminder of how temporary everything is, how much the world has changed, and how much it will change again. And here's something astonishing. Hidden deep in tiny crystals of ancient minerals, scientists have found chemical whispers of that first atmosphere. Ratios of isotopes preserved like fingerprints telling us what gases filled the air, how hot it was, how violent the storms must have been. We can't time travel to see those skies directly, but these microscopic messengers bring us close. It's almost like holding a souvenir from a planet we'd never recognize. So picture it. The world covered in fire and smoke storms without rain, skies without stars. A place unfit for any life but pregnant with possibility. Because within that atmosphere, the ingredients for transformation were brewing. The stage was set for rain oceans and eventually life. For now, though, we linger in the smoke in the heavy breath of a newborn planet, knowing the storm to come will not destroy but create. The first rains on Earth were not delicate showers. They weren't the gentle patter on a roof that lulls you to sleep, or the kind of drizzle you might curse while waiting for the bus. No, these rains were torrential, relentless, and they lasted not for days or weeks, but for thousands upon thousands of years. 2. Imagine them. You have to leave behind every experience of rain you've ever had. Picture clouds so dense and heavy, they turned the skies black for centuries, pouring down water with such force it would have carved the land into wounds of stone. But let's rewind slightly. Before the rain began, the atmosphere had to change. Remember those volcanoes? They were the engines. For millions of years, they exhaled gases. Steam, carbon dioxide, hydrogen, sulfur compounds into the sky. With the Earth's crust still thin and cracked volcanic vents were everywhere, steam gathered clouds, thickened, and eventually the tipping point was reached. When the surface cooled just enough, when the sky was heavy with water vapor, it began. And it didn't stop. Imagine standing at a safe distance, not that such a place truly existed, and watching the first drops fall onto a searing crust. The contact would have been dramatic: water instantly vaporized, hissing and exploding into steam. Each raindrop was like a kamikaze sacrificing itself to cool the world below. But as the planet's surface slowly lost heat, more and more of that water survived, collecting in cracks, pooling in basins, flowing together. That's how the first oceans were born. Oceans not of blue serenity, but of boiling fury. Here's a quirky fact. Some scientists suggest those rains may have lasted for as long as 10,000 years without pause. Picture that. Day after day, century after century, rain hammering against molten stone, filling the newborn earth with water. If you think the rainstorm that ruined your weekend was bad, imagine 10 millennia of non-stop downpour. Talk about bad luck for picnics. There's an ongoing academic argument about the exact source of that water. Was it mostly from inside the planet, released by volcanic outgassing? Or did a portion of it come from beyond, delivered by icy meteorites crashing into Earth? The truth is probably both. Volcanoes gave us steam, asteroids gave us ice, and together they rained oceans onto the Earth. The debate continues, but either way, the result is the same. A planet once ruled by fire became a planet ruled by water. Now let's talk about how those first oceans must have looked. They weren't the sparkling turquoise waters you see on postcards. They were acidic, steaming, dark, filled with dissolved minerals from the relentless weathering of hot rock. Rivers of rainwater carried iron and sulfur into the seas, turning them greenish or even rusty red. Lightning forked constantly across the skies, igniting chemical reactions in the atmosphere, striking the oceans, stirring up strange brews of molecules. These storms weren't destructive, they were creative. They were chemistry experiments written on a planetary scale. And in those early seas, something remarkable was happening. Molecules of hydrogen, carbon, nitrogen and oxygen were colliding, combining, breaking apart and recombining. Tiny organic compounds began to form amino acids, the building blocks of life. They weren't alive yet, but they were seeds scattered in the broth of the world's first oceans. Every raindrop that fell carried not just water, but possibility. I like to imagine the sound of it all. Not just rain, but a symphony. The endless roar of downpour, the hiss of steam, the crack of thunder, the bubbling of boiling seas. It must have been deafening, overwhelming. And yet, within that noise was the quiet whisper of life's beginning. Here's a strange side note you might enjoy. Scientists have recreated miniature versions of this scenario in laboratories by zapping mixtures of gases with electrical sparks simulating lightning in the early atmosphere. They've produced amino acids, the same molecules your body uses today to build proteins. It's as if the recipe for life was written into the storm itself. That discovery doesn't mean we fully understand how life began, but it does suggest that the ingredients were mixing long before biology had its first heartbeat. And think of the paradox here, rain, which we usually see as cleansing or destructive, was the great creator. Without that endless deluge, Earth would have remained a barren rock wrapped in fire. Instead, it became a water planet draped in seas that would eventually cradle continents, guide climate, and nurture life. But the transformation wasn't instant. After the first oceans formed, Earth still looked alien. Continents didn't exist yet, just a thin crust that cracked and reformed constantly. Oceans spread across nearly the entire surface, shallow in some places, unimaginably deep in others. The skies, though clearer, were still heavy with gases no human could breathe. The sun was dimmer, the nights darker, the storms violent. But in that setting, something new was possible. The stage was finally ready for chemistry to become biology. Let me lighten the mood with a modern joke. If you had been alive during those rains, which you wouldn't, because you'd be boiled alive in about 3 seconds, your weather app would have given up after day 3. Rain today, rain tomorrow, rain forever. Don't bother checking again. Maybe the only push notification would have been upgrade your umbrella plan. It's humbling to think that every river, every lake, every sip of water we drink today is part of that same cycle. The drops that fell 4 billion years ago didn't vanish. They flowed into oceans, evaporated, condensed and rained again. They've been recycled countless times. Some of the water in your glass tonight may once have boiled on newborn Earth, may once have fallen in the first storm that ever touched this planet. So when we talk about the first rains, we aren't just describing a moment in history. We're describing the baptism of Earth, the moment fire yielded to water and chaos began to cool into balance. This wasn't just weather, it was destiny. The rains sculpted oceans, and oceans would soon sculpt life. And as the clouds thinned and the world began to settle, the next chapter was waiting. Written not in storms, but in crystals. Tiny, ancient messengers carrying the first whispers of a planet ready to change forever. Whispers in tiny crystals, doesn't that sound poetic? But this isn't poetry. Not really. It's geology, science at its most delicate. You see, some of the most ancient voices of our planet aren't towering mountains or massive canyons. They're microscopic crystals called zircons. These tiny slivers, no bigger than grains of sand, hold secrets billions of years old. When geologists peer into them, they're not just looking at pretty stones. They were reading diaries written by the Earth itself. Now what makes zircons so special is their durability. While most rocks are ground down, melted or recycled back into Earth's restless crust, zircons endure. They survive the chaos, carrying inside them isotopic fingerprints of the conditions they were born in. Some zircons have been dated to 4.4 billion years ago, just 100 million years after Earth itself formed. That's ancient beyond imagination. And locked inside these crystals are whispers of something shocking. Liquid water existed on Earth much earlier than we once believed. Pause on that thought. For decades, scientists assumed Earth's first few 100 million years were nothing but fire oceans of magma, an atmosphere of toxic fumes, surfaces constantly shattered by impacts. The very name of that time, the Hadean Eon, comes from Hades, the underworld. It was supposed to be hell. But zircons tell another story, a quieter one. The ratios of oxygen isotopes inside them suggest those crystals interacted with liquid water, rain, or oceans that must have existed around 4.3 to 4.4 billion years ago. That's impossibly early compared to old models. The Earth, it seems, cooled faster, calmed sooner, and grew wet earlier than anyone expected. There's a delightful academic debate here. Some researchers insist zircons prove that stable crust and oceans existed astonishingly early. Others argue the evidence is more ambiguous, that zircons may reflect isolated conditions, not global seas. But whether it was puddles or oceans, the fact remains water touched this earth far earlier than the hellscape-only story allowed. And I love that. It's a reminder that even in what we call chaos, gentleness can find a way in. Let's go deeper into what these crystals really mean. Inside zircons, you find not just oxygen isotopes, but tiny inclusions, minute fragments of minerals trapped like insects in amber. Some inclusions point to cool, wet conditions minerals that form only when water interacts with rock. Others hint at continental crust forming earlier than expected. That suggests Earth didn't remain a featureless ocean world for long. Land might have poked its head above the waters, sooner islands breaking the endless seas. Even if brief, they would have changed the chemistry of the oceans, creating more varied environments where life's experiments could later unfold. Here's a quirky side note. Zircons are so tough that geologists sometimes joke they're the cockroaches of minerals. You can crush mountains, boil oceans, blast planets with impacts, but zircons hang on tiny time travelers carrying secrets across billions of years. They don't just resist destruction, they thrive on being witnesses. And unlike cockroaches, people actually want to study them. Think about how absurdly fragile this evidence is. One microscopic crystal invisible to the naked eye can overturn centuries of assumptions about our planet. It's humbling, almost comical. Imagine finding a diary note in a teenager's notebook that rewrites all of human history. That's the scale of impact we're talking about. These zircons tell us Earth wasn't just a flaming ball of doom for eons. It was more complex, more nuanced. There were moments of cool, moments of wet, moments of possibility. And those moments mattered. Because if water appeared early, then the chemistry of life could have started earlier too. Maybe not full-fledged organisms, but the groundwork, the amino acids, the lipid bubbles, the primitive chains of RNA. Life didn't need perfect oceans. It needed time and variety. Early water gave it both. Now, let me paint the picture of how scientists actually read zircons. It isn't with magnifying glasses and tweezers. They use instruments like ion microprobes, shooting beams of particles into crystals to tease out isotopes. Imagine interrogating a criminal who refuses to speak, and instead of words you get ratios oxygen 18 compared to oxygen 16 hydrogen compared to deuterium. These ratios become the language of the past whispers from the Hadean Eon. It's detective work on an atomic scale. Of course, no story is complete without a twist. Some zircons suggest cool conditions, but the broader geological evidence still screams of violence. Giant impacts were common. Lava oceans likely resurfaced Earth multiple times. So, how do you reconcile the two pictures? The answer may be that Earth flipped between extremes, sometimes boiling, sometimes cooling, sometimes wet, sometimes dry. The zircons may capture fleeting windows of calm amid the chaos. To me, that makes the story even richer. Earth wasn't a monotone furnace. It was a restless teenager, moody and inconsistent, but gradually growing into balance. Let me throw in a little modern joke here. If Earth kept a weather journal back then, it might have read like a teenager's diary. Day 1, still boiling. Day 2, so much rain. Day 3 got hit by another asteroid. Ugh, nobody understands me. And those zircons, they're the notes that survived tucked away in the margins. What fascinates me most is how this discovery reshapes our sense of time. If oceans existed at 4.3 billion years ago, then life could have had a 700 million year head start before the fossil record even begins. Think of how much can happen in 700 million years. Dinosaurs rose and fell in less than half that. Entire continents shifted climates. Swung ecosystems transformed all in less time than those early oceans may have had to nurture chemical experiments. Life might have begun trying, failing and trying again long before we'll ever know. And here's the kicker. Zircons also hint at tectonic activity. Plate tectonics, that grand churning of Earth's crust, may have started earlier than believed. Water plays a critical role in lubricating subduction, the process where crust sinks back into the mantle. If water was present, tectonics may have started stirring earlier, recycling nutrients, stabilizing climates, and creating environments where complexity could flourish. Without tectonics, Earth might have remained static like Mars. With it, the stage was dynamic, ever-changing, fertile. So these little crystals don't just tell us Earth had water. They hint that Earth was already acting like Earth, restless, creative, alive in its geology. And because they survived, we can piece together this ancient whisper, the faint beginnings of oceans, rain and crust. It's incredible, isn't it? From a single grain, we glimpse a planet not just fiery, but also wet, not just hellish, but also hopeful. We realize that Earth's story has never been one of pure chaos or pure calm, but of both woven together. And in those tiny whispers lies the first hint that life's canvas was ready, stretched and primed, waiting for the brush of biology. As we hold those zircons up to the light in a lab, we are in a way holding the memory of a world we could never have survived, in one that shaped us entirely. A world that was already wet, already stirring with the raw ingredients of tomorrow. And that whisper leads us straight into the next chapter, when Earth stopped merely cooling and began to endure the heaviest bombardment it would ever face, an era of rock ice and fire raining down from the skies. The Late Heavy Bombardment. It sounds like the title of a rock band, but in truth, it was one of the most brutal chapters in Earth's history. Picture this: between 4.1 and 3.8 billion years ago, our planet endured a ceaseless rain of asteroids and comets. Not little shooting stars you might wish upon, but mountain-sized projectiles, slamming into Earth at speeds so violent they could vaporize oceans and melt entire regions of crust in an instant. It was as if the cosmos had opened a firing range, and Earth was the prime target. The solar system was young and messy, then still reorganizing itself after the giant planets Jupiter, Saturn, Uranus, Neptune had shifted into their present orbits. Those gravitational giants played a cruel game of cosmic pinball, flinging icy bodies and rocky debris inward toward Earth, Venus, Mars and Mercury. For Earth, the result was catastrophic and transformative. Every few thousand years, a new impact would scar the planet, shatter crust, boil seas, and release clouds of dust that blacken the skies. Here's a quirky detail to keep in mind. Some scientists still debate whether the late heavy bombardment was a distinct event or whether impacts simply tapered off gradually. The lunar surface, scarred by ancient craters, offers most of our evidence. The moon, lacking plate tectonics and weather to erase its wounds, still bears the pockmarks of those violent years. By dating lunar rocks brought back by Apollo missions, geologists traced a cluster of ages around 3.9 billion years ago. That cluster became the smoking gun for a concentrated bombardment. But others argue the evidence could also reflect sampling bias. After all, Apollo missions only visited certain regions. The academic debate rages on, but either way, there is no doubt Earth was pummeled relentlessly in those early days. Imagine oceans already forming from the endless rains we spoke of in Part 4. Now picture those oceans being vaporized again and again by giant impacts. One colossal strike could turn seas into steam, sending tsunamis hundreds of miles high rippling across the surface. If you think hurricanes are bad, imagine a wave taller than Mount Everest racing around a molten shoreline. The sky itself would ignite with shock waves, and the surface would glow from the sheer energy released. It's destruction on a scale our minds can barely hold. And yet, paradoxically, those same impacts may have delivered precious cargo. Many of the asteroids and comets slamming into Earth carried water, organics, and minerals. Each collision wasn't just a hammer. It was also a gift basket, bringing the raw ingredients for chemistry and life. Scientists studying carbonaceous chondrites, primitive meteorites, find they contain amino acids, sugars, even building blocks of DNA. So yes, the bombardment boiled oceans, but it may also have spiced them with the recipes for biology. Here's a fun modern joke. If Earth had Yelp reviews back then, the comments would read, "Too violent." "Got smacked by another asteroid today. 1 star. Would not recommend." But hidden beneath the sarcasm, those reviews would also admit free delivery of amino acids included. Think about how this shaped Earth's identity compared to our neighbors. Mercury and the Moon were pummeled too, but lacking thick atmospheres or active geology. They froze in their battered states. Mars endured impacts, but its smaller size meant it lost heat and atmosphere more quickly. Earth, by contrast, was big enough, hot enough, and dynamic enough to heal. Its crust recycled itself through volcanic activity and tectonic churn. Its atmosphere replenished through outgassing. Oceans returned after being vaporized. The planet absorbed the punishment, but it bounced back stronger. That resilience may be the reason life could take root here and not elsewhere. Let me weave in another strange aside. Some scientists suggest the bombardment may have created temporary niches where life could begin. When an asteroid slammed into the ocean, it didn't just cause destruction. It also created hydrothermal systems, hot mineral-rich environments ideal for chemistry. Picture deep craters filled with boiling water and minerals, little laboratories scattered across the planet. Life may have emerged from these very crucibles of chaos. It's hard not to feel humbled when you realize that every living thing today, every tree, bird, human, owes its existence to this strange paradox. Violence delivered nurture. Destruction paved the way for creation. Earth wasn't spared from the cosmic storm, it was shaped by it. Now picture standing at the edge of one of those ancient seas as an asteroid slams into the horizon. The flash is brighter than 1,000 suns. The shock wave rattles your bones, and then comes the wall of water rushing toward you faster than sound. You wouldn't survive, of course, but the planet would. And in surviving, it became what it is, a world sculpted by fire, rain, and stone cradling oceans that carried the first whispers of life. And here's the most point-bending thought of all the water you drink today. The very molecules swirling in your glass may have arrived in part during that bombardment. Some droplets may have been locked in asteroids for billions of years before splashing onto Earth's surface. In every sip, you taste a fragment of cosmic history. So the late heavy bombardment wasn't just a nightmare, it was a forge. It broke Earth again and again, but each time the planet rose from the blows, more capable of sustaining life. By the time the impacts waned, Earth was no longer just a ball of rock wrapped in storms. It was a world drenched in oceans, seasoned with organics and trembling with potential. The canvas was nearly ready for the next act, a hidden chemistry brewing beneath the seas, setting the stage for life's first experiments. By the time the bombardment slowed, Earth had become something new, a water world. Not quite the serene blue planet you'd recognize from space today, but one draped in endless oceans, shallow seas, stretching across most of its surface. Continents as we know them hadn't yet formed. Instead, jagged volcanic islands poked out here and there like the teeth of some giant creature breaking the surface. The skies above, still heavy with carbon dioxide and methane, cast the world in strange hues, red, orange, and murky brown rather than blue. But for the first time, Earth was more water than fire. And this water wasn't quiet. The oceans were chemical cauldrons, simmering under the dim glow of a younger sun. Dissolved minerals streamed in from the land, carried by relentless rain. Iron turned the seas greenish. Sulfur added its own bitter tang. Lightning forked across the skies, striking the oceans again and again, each flash sparking chemical reactions. The seas weren't just passive. They were laboratories experimenting endlessly with molecules. Here's a quirky fact. Modern experiments like the famous Miller-Urey experiment of the 1950s have shown that if you zap a mixture of gases similar to early Earth's atmosphere with electrical sparks, you can create amino acids, the building blocks of proteins. In a few days, a simple setup in a lab generated compounds essential for life. Now stretch that over millions of years across oceans, the size of worlds, and you start to see why scientists believe life's first whispers emerged here. But here's where academic debate sparks lively arguments. Some researchers argue that life's chemistry began in these warm little ponds at the ocean's edges, where evaporation and concentration created fertile ground for complex molecules. Others insist the real birthplace was deep underwater at hydrothermal vents, those volcanic chimneys that spew mineral-rich water heated by Earth's mantle. Still others wonder if the seeds of life rode in on asteroids, a cosmic delivery service, dropping off organic molecules ready to assemble. The truth, we don't know yet. But maybe it doesn't matter, because what we do know is that Earth gave life more than one possible doorway. Imagine standing at the shore of one of those early seas, well floating there, because standing would have been impossible. The air thick with gases you couldn't breathe, the water warm, almost hot, rippling with strange colors. If you could zoom in close enough, down to the microscopic scale, you might see molecules bumping, twisting, and colliding, some sticking together, others breaking apart. Random chaos. Yes, but chaos with potential. That's the beauty of chemistry. It doesn't need purpose to create wonders. Now, here's a humorous aside. If you think modern cooking shows are experimental, with chefs foaming and smoking dishes, imagine Earth's oceans as the ultimate kitchen. Ingredients: hydrogen, carbon, nitrogen, oxygen, and a sprinkle of sulfur. Tools: lightning heat pressure. Recipe leave to simmer for a few 100 million years. Result: life. No Michelin stars required. But while the seas experimented the land, what little there was also played a role. Early volcanic islands provided surfaces where minerals could concentrate and react. Clay, in particular, may have helped assemble complex molecules by acting like a template, encouraging smaller pieces to link together. It's humbling to think that something as unglamorous as clay might have been a midwife to life. The oceans of this era were strange in other ways too. With no free oxygen, they were reducing environments, meaning they preserved molecules that would otherwise break down quickly today. Iron dissolved freely in the waters, only later to rust when oxygen arrived. Methane bubbles may have risen from deep below, creating shimmering layers on the surface. The seas were alien, yes, but perfectly suited for chemistry. Here's another curious side note. Some scientists believe Earth's oceans may actually contain water older than the sun itself. The hydrogen in water molecules was forged in the Big Bang over 13 billion years ago. That means when you drink a glass of water, you're sipping on atoms that have traveled across cosmic time, older than the Earth, older even than the solar system. That kind of thought makes you pause before swallowing, doesn't it? So the oceans became crucibles, brewing chemistry, not in one place, but everywhere, but everywhere. Shorelines, vents, surface pools, even inside droplets of rainwater mixing with volcanic gases. Slowly, slowly, simple molecules formed more complex ones. Amino acids linked into peptides. Fatty molecules arranged themselves into bubbles, creating tiny, fragile containers. Inside these bubbles, other molecules gathered, reacting in ways they couldn't outside. These little bubbles weren't alive, but they were steps on the road to life, miniature worlds practicing existence. It's fascinating, isn't it? Earth had endured fire bombardment storms and deluge only to arrive at this moment, a quiet, patient chemistry, working in the background. No fanfare, no drama, just molecules following the laws of physics and chemistry, guided by chance and repetition. And yet, in that silence, the foundation of everything we know, forests, oceans, humanity, was being laid. Think about how long this phase lasted. Hundreds of millions of years of trial and error, of molecules forming and breaking, of oceans simmering. Most attempts at complexity probably failed. But every now and then something lasted a little longer, survived a little better, repeated itself. Those repetitions, those survivors carried the torch forward. By the end of this chapter, Earth wasn't just a water world. It was a world of potential. Oceans stretched across its surface, clouds drifted above volcanoes, shaped the land, and chemistry churned below the waves. The stage was fully set. The next step wouldn't be simple molecules. It would be the first fragile sparks of life itself. Life didn't begin with a bang. It began with whispers, tiny, fragile, almost accidental whispers. After hundreds of millions of years of chemistry, Earth's oceans started to see the emergence of something new molecules that didn't just exist, but copied themselves. That was the leap, the turning point, the moment when chemistry edged into biology. And it's strange to think it wasn't inevitable. It was the luck of the draw, a lottery ticket won by a molecule in a warm, bubbling sea 4 billion years ago. Picture Earth, then endless oceans tinted green by dissolved iron volcanic islands steaming in the distance, lightning flickering across dark skies. Deep below the waves, near hydrothermal vents, water superheated by the mantle gushed out, mixing with colder seawater, creating rich mineral-laden gradients. These vents weren't just fountains of heat, they were engines of possibility. Within their chimneys of iron and sulfur, chemistry found niches to explore. Hydrogen flowed, carbon compounds collected, and tiny pores inside the vents may have acted like natural test tubes, encouraging molecules to organize. Some scientists argue this was the birthplace of life at these vents where heat and chemistry danced together. Others push back, suggesting life may have begun in shallow pools on the surface where cycles of wet and dry concentrated molecules in ways deep oceans never could. And here we land in one of science's most passionate debates: vents versus ponds, deep sea versus shorelines. Honestly, both sound plausible, and maybe both were true. Perhaps life tried multiple doorways and one succeeded. Here's a quirky thought. Whichever environment gave us life, it had to solve the same problem: replication. Without replication, chemistry is just static. With replication, you get competition, variation, and evolution. Some believe RNA, a molecule capable of storing information and catalyzing reactions, was the key. RNA is like DNA's scrappy, older sibling, less stable but more versatile. Imagine strands of RNA forming in those oceans, copying themselves imperfectly, creating slight variations. Some versions broke apart quickly, others lasted longer. The survivors multiplied. That right there was the birth of evolution. Now let's step sideways for a moment. Did you know scientists have actually coaxed RNA strands in labs to replicate and evolve? It doesn't look like life as we know it. It's more like little spaghetti strands competing in a soup. But it's enough to suggest the principle works. Replication breeds complexity. And if it works in a lab today, why not in an ocean? 4 billion years ago. Of course, replication alone wasn't enough. Molecules needed protection. That's where fatty acids came in. These simple molecules naturally form bubbles in water called vesicles. Inside those bubbles, fragile RNA or peptides had shelter, a safe space where reactions could happen without being destroyed instantly. These bubbles were the first cells, though calling them that is generous. They were flimsy, unstable, popping as easily as soap bubbles, but they were the ancestors of every cell alive today. Imagine it. Microscopic bubbles, floating in Earth's oceans, dividing, merging, breaking apart. some carrying molecules that could replicate. They weren't alive in the way we think of life, but they were on the cusp, teetering on the edge of animation. If you could scoop up a handful of seawater then and peer at it with a super microscope, you'd see chaos bubbles bursting strands of RNA, copying badly peptides, clumping together. And yet, among that chaos persistence, some lasted long enough to matter. Some repeated long enough to leave echoes. Here's a humorous aside. If those first protocells had Instagram accounts, their bios would have read, "just a bubble trying not to pop." Still evolving. Not exactly influencer material, but hey, they were trendsetters of existence. The oceans of that time weren't just passive backdrops. They were active players, stirring chemistry with currents, heating it with vents, electrifying it with storms. Every drop of water carried molecules that could collide and recombine. Every shoreline, every vent, every puddle was a lab. And Earth had time. Millions of years of experiments, countless failures, occasional successes. Failure wasn't the end. It was part of the process. Every time a strand broke apart, its pieces fed another attempt. Every time a bubble burst, it seeded the sea with materials for the next bubble. Out of failure, persistence was born. Here's another fascinating detail. The earliest oceans were rich in metals like iron and nickel. These metals may have acted as catalysts, encouraging reactions that otherwise wouldn't happen. In other words, the ocean wasn't just water. It was a brew laced with natural chemistry kits guiding molecules toward complexity. It's almost as if the planet was rooting for life, nudging molecules along. Though, of course, it was just physics and chemistry doing what they do. Still, the coincidence feels uncanny. Eventually, those fragile bubbles and strands crossed a threshold. They weren't just random molecules anymore. They were systems, tiny, fragile, self-sustaining systems. They could grow, divide, compete, and change. That's the moment life was born. It didn't roar into existence. It whispered into being, carried on the backs of oceans and storms. And think about this. All of it happened in darkness. The sun was weaker. Then the atmosphere choked with haze. Light struggled to reach the seas, and where it did, it was filtered and strange. Life's beginnings were hidden, unseen, cradled in shadows. That feels poetic to me, that the story of all living things began not in brilliance, but in obscurity, not in grandeur, but in secrecy. By the time the first true cells emerged, simple single-celled organisms, they inherited the oceans as their kingdom. They fed on chemicals, not sunlight, living off the gradients of energy near vents or the soups of organics in shallow seas. They were tiny, invisible, humble. And yet, they were the ancestors of everything to come. Trilobites, dinosaurs, oak trees, whales, us. Life had finally crossed the line from chemistry into biology, and though it was invisible to the naked eye, its presence began to ripple across the planet. These earliest organisms, prokaryotes, simple single-celled beings without nuclei, were astonishingly resilient. They lived in conditions that would kill nearly anything alive. Today, acidic waters, scalding vents, radiation-bathed shallows. To us, they seem fragile, but in truth, they were hardy pioneers carving out existence on a world that was still more hostile than hospitable. Let's imagine their world. The oceans were their universe, dark and vast. Sunlight filtered only into the surface layers, and even then, the skies above were hazy painted orange by methane. Below, hydrothermal vents belched out hot mineral-rich water, creating ecosystems powered not by light, but by chemistry. These cells didn't need oxygen. It wasn't there yet anyway. Instead, they thrived on chemical reactions pulling energy from hydrogen, sulfur, and iron. This was a planet alive in the shadows. Here's the quirky part. If you traveled back in time with a glass jar and scooped up some seawater, you might not even notice anything inside. No fish, no plants, no algae, not even recognizable slime. Yet, within that jar would be the entire population of Earth's living world. Billions of tiny cells, invisible, humming with the first sparks of metabolism, replicating, competing, evolving. It would look like nothing, but in reality, it was everything. Academic debates swirl around how diverse life was at this stage. Some argue there may have been multiple origins of life, different molecular systems arising independently in different places. Most failed, leaving no descendants. One lineage endured, and from that lineage, everything else followed. Others counter that life emerged once narrowly, and that its survival was a miracle against impossible odds. The tension between inevitability and contingency is one of the deepest questions in biology. Was life destined given the conditions, or are we the product of an almost impossible fluke? Now let's bring in a curious side note today. Deep inside the Earth's crust, miles beneath the surface, there are still microbes living in darkness, feeding on rock hydrogen and chemical gradients. They don't need sunlight at all. In fact, some scientists suggest that they might have originated not in open seas or shallow ponds, but underground in the porous rocks of Earth's crust. There, shielded from impacts and radiation, life could have quietly taken root. The idea may sound strange, but remember, microbes today thrive in boiling vents, acidic lakes, frozen glaciers, and even inside nuclear reactors. Life doesn't ask for comfort, it asks for opportunity. Imagine being one of those first microbes. Not that you could imagine anything. Your world is limited to the thickness of a cell wall. Your interactions are bumping into molecules, your goals, nothing more than survival and replication. Yet in the tiny, mindless persistence lies the seed of all future complexity. Every plant leaf, every whale song, every human thought began with organisms that had no thoughts, no senses, no plans. Just the blind mechanics of chemistry repeating endlessly. Now, here's where the story gets interesting. Evolution began to flex its muscles. Those first cells weren't perfect, and mistakes happened when they copied themselves. We call them mutations today, but back then they were the raw material of progress. Some mutations made cells weaker, and those cells died. Others gave tiny advantages, a faster enzyme, a sturdier membrane, a better way to harvest energy. Those cells lasted longer, reproduced more, and passed on their quirks. Over millions of years, quirks piled up into changes, and changes stacked into diversity. Life was no longer a single whisper, but a growing chorus. Here's a humorous aside. If natural selection had a slogan, back then it would have been "copy badly, survive." Well, mistakes weren't just tolerated, they were the secret sauce. Without mistakes, evolution doesn't happen. So the next time you beat yourself up for making an error, remember mistakes made you possible. The oceans grew richer with life, though rich is relative. We're still talking about a world of microbes no larger than dust motes. But these microbes started to shape the very chemistry of Earth itself. They altered oceans, shifted gases, and began cycles that continue to this day. Some microbes learned to use sunlight, developing the ability to capture energy through photosynthesis. But, and here's the key, it wasn't oxygenic photosynthesis yet. They weren't making oxygen. Instead, they used other molecules like hydrogen sulfide to power their reactions. The oceans filled with volcanic gases were perfect for this. But then, something revolutionary happened. Somewhere in some shallow sea or coastal mat, a group of microbes developed a way to split water molecules with sunlight. This was a radical invention. Water was abundant everywhere, and by splitting it, they tapped into an almost limitless energy source. The waste product, oxygen. And with that waste, the fate of Earth was sealed. At first, oxygen didn't accumulate in the air. It reacted with iron in the oceans, rusting it into red bands of rock that geologists still find today. Banded iron formations, silent fossils of the planet's first breaths. But eventually, the iron was used up and oxygen began to leak into the atmosphere. Slowly, invisibly, the air transformed. And that transformation would change everything, paving the way for complexity, but also unleashing the first mass extinction in history. Before we leap ahead, pause with me. Think of the irony microbes too small to see, with no awareness or intention altered the entire planet's chemistry. They weren't trying to shape Earth, they were just eating, surviving, copying. And yet, they rewrote the planet's destiny. That's the power of life, even at its most humble persistence. Plus, time equals transformation. Here's one last quirky note for this chapter. Scientists studying stromatolites, layered rock structures built by microbial mats, have found fossils over 3.5 billion years old. These stromatolites, which still form in a few places today, are monuments to the first communities of life. Imagine reefs not of coral, but of microbes stacking themselves into domes, layer after layer, like ancient architects leaving blueprints for the future. They're quiet, unassuming, but they whisper to us across time. We were here. We began it all. And so, by this point in Earth's story, life wasn't just clinging on. It was multiplying, diversifying, and starting to leave scars on the planet itself. The next great act would come with oxygen, a gas that would bring both death and opportunity, forcing life into a crucible of change that would define everything to come. It's wild to consider how fragile it all was. A few unlucky asteroid strikes, a few changes in chemistry and life might never have gained a foothold. Earth could have remained barren, a sterile water world. But it didn't. Against all odds, molecules, organized bubbles, held replication, succeeded. And here's a quirky side note to close this chapter. Some scientists think if we rewound Earth and played it again, life might not happen the same way, or at all. Others argue it was inevitable that with water chemistry and time, life always emerges. The truth, we may never know. But sitting here billions of years later, sipping coffee brewed with ancient water molecules, it's hard not to marvel. We are living proof that at least once it worked. By the close of this chapter, Earth was no longer just a planet with oceans. It was a living world, even if life was microscopic and invisible. And from that point forward, biology would never leave. It would adapt, change, evolve, and reshape the planet itself. The next steps wouldn't be quiet chemistry. They would be planetary revolutions driven by cells too small to see, but powerful enough to transform everything. The rise of oxygen. What a paradox! A gift and a curse wrapped into one invisible gas. Up until this point, Earth's biosphere had been a playground for microbes that loved a world without oxygen. They thrived in methane-rich seas, in iron-heavy oceans, in skies cloaked with haze. Oxygen was toxic to them, a molecular assassin that destroyed the delicate chemical reactions on which they depended. And yet, once photosynthetic microbes figured out how to split water molecules and release oxygen, there was no turning back. The floodgates had opened. At first, the oxygen didn't drift far. It collided with the iron dissolved in oceans, oxidizing it into rust. Picture seas stained with red iron minerals falling to the seafloor in thick layers. Over millions of years, these reactions created the banded iron formations we still mine today. Each layer is like a pulse, a heartbeat of Earth, recording how much oxygen was being pumped into the environment. For a while, this process kept the atmosphere free of oxygen like a sponge soaking up a spill. But sponges eventually fill. And when the iron was gone, the oxygen had nowhere else to go. It began to accumulate in the skies. That slow buildup of oxygen was a revolution, but not a gentle one. For many of the microbes alive, then oxygen was poison. It tore apart their cellular machinery, disrupted their metabolic processes, and turned their cozy anaerobic world into a nightmare. What followed is sometimes called the Great Oxidation Event. Around 2.4 billion years ago, the planet's first mass extinction. Trillions of microbes perished, their lineages erased. Entire ecosystems collapsed. To them, oxygen wasn't a promise of the future. It was the end of the world. But death for some was opportunity for others. A new kind of metabolism emerged, aerobic respiration. Unlike anaerobic processes, which extract little energy from food, aerobic respiration is powerful. With oxygen, cells could unlock far more energy from the same resources. That energy surplus became the foundation for complexity. Bigger cells, faster growth, more intricate structures all became possible because oxygen was now in the air and water. Here's the strange twist. Life didn't just survive oxygen, it turned oxygen into its greatest ally. Think of it like this. Oxygen was a deadly fire, but some microbes learned to tame it, to use its flame without being consumed. In doing so, they became the ancestors of all complex life. Every breath you take, every beat of your heart, every thought in your mind is powered by oxygen. We are descendants of the survivors of that first global catastrophe. Let me drop a quirky side note here. Oxygen is actually a weird gas. Too little, and life suffocates too much, and the planet catches fire. Around 300 million years ago, oxygen levels rose so high that dragonflies grew wingspans the size of hawks. Imagine walking outside and swatting away a bug the size of a dinner plate. The balance is delicate, and Earth has walked that line for billions of years, back to the ancient world. As oxygen levels rose, the chemistry of Earth shifted dramatically. Methane, once abundant, was broken down by oxygen, weakening the greenhouse effect. The result, A deep freeze. Ice spread across the globe, perhaps all the way to the equator. Scientists call these episodes snowball Earth events. Imagine oceans frozen, nearly solid continents buried under glaciers, sunlight bouncing off a reflective white world. To us, it sounds like extinction again. But somehow, life endured, tucked away in cracks, vents, and liquid refuges beneath the ice. Survival was possible, but brutal. Academic arguments flare here too. Some say the entire planet froze solid. Others think equatorial regions remained open. Either way, these global chills were tied directly to oxygen's rise and the decline of methane. Oxygen didn't just transform life, it reshaped the planet's climate itself. But oxygen's influence reached deeper still. With more energy available, cells began to grow more complex. Somewhere around 2 billion years ago, a remarkable merger occurred. One cell engulfed another, and instead of digesting it, the two formed a partnership. That engulfed cell became the mitochondrion, the powerhouse of modern cells. This event, endosymbiosis, was perhaps the most important handshake in history. Without it, complex multicellular organisms might never have existed. Picture that moment. A hungry cell swallows another expecting lunch, but instead gains a roommate. The roommate offers a trade. Don't digest me, and I'll give you energy, lots of it. The host agrees, and together they thrive. Billions of years later, every plant, animal, and human cell still carries that ancient alliance inside mitochondria, humming away, producing energy with oxygen. It's almost funny if you think about it. The greatest innovation in evolution wasn't a new body plan or a new skill. It was a truce, a peace treaty between two microbes. And from that treaty, complexity exploded. Meanwhile, oxygen also paved the way for another miracle, the ozone layer. As oxygen accumulated, some of it formed ozone high in the atmosphere, creating a protective shield against harmful ultraviolet radiation. Before that, life was confined to oceans and shadows, shielded from the sun's deadly rays. With ozone in place, the surface became less hostile, opening new possibilities for life's eventual expansion onto land. Here's another quirky aside. Scientists once thought oxygen rose in a steady, smooth curve. But evidence suggests it spiked and crashed up and down like a roller coaster. Oxygen wasn't stable for hundreds of millions of years. It surged, collapsed, and surged again. Imagine trying to live through that one generation after another, not knowing if the very air around you would nurture you or kill you. So let's step back and see the bigger picture. Oxygen, born as a waste product of microbial photosynthesis, reshaped every system of Earth. It killed off huge swaths of life. It froze the planet. It altered the atmosphere. And yet, it laid the foundation for everything to come. Without oxygen, there would be no forests, no dinosaurs, no humans. Without oxygen, Earth might have remained a microbial world, forever limited to simple cells. And here's the thought that lingers: oxygen reminds us that survival isn't always about comfort. Sometimes survival means enduring catastrophe, adapting to poison, and finding a way to use what once killed you. Those early microbes didn't set out to invent complexity. They simply found ways to keep going. In doing so, they gave us the world we know. Now imagine standing on Earth during that age. The seas still greenish from iron but slowly clearing. Stromatolite reefs rising in shallow waters built by microbial mats. The skies for the first time tinged faintly blue as oxygen crept upward. The air wasn't breathable by our standards, not yet, but the seeds of the future were sown. In the silence, in the slow churn of tides and wind, Earth was beginning to change from a microbial playground into a planet on the cusp of complexity. And from here, the story only grows grander. Cells will evolve into new forms. Multicellularity will spark. Organisms will grow, reproduce, and eventually crawl toward the light. But none of it would have been possible without this paradoxical revolution. The rise of oxygen, a poison turned into power, a catastrophe turned into creation. The Great Oxidation event had set Earth on a new trajectory, one no longer defined solely by chemistry, but increasingly sculpted by biology. Oxygen was both the scythe and the soil, cutting down the old and fertilizing the new. In its wake, life began to experiment in ways it never had before. The world was no longer a closed stage for microbes surviving in shadows. It was becoming a place where complexity could bloom. Let's slow down and imagine Earth around 2 billion years ago. The skies were no longer choked orange with methane. Instead, for the first time, they began to hint at the faintest shades of blue, the color we take for granted today. Oceans still dominated the surface, but they were subtly transforming too, less iron-rich, clearer shifting chemically to favor organisms that could tolerate or even thrive in oxygen. Along coastlines, microbial mats continued their quiet construction projects, stacking themselves into stromatolites, leaving signatures still visible in rocks today. But beneath the waves, something new was stirring. Inside cells, a revolution had taken hold. That merger. I mentioned the endosymbiotic pact that created mitochondria wasn't just a novelty, it was a revolution. Imagine life suddenly gaining access to an energy economy 10 times richer than before. Aerobic respiration allowed cells to do more, grow larger, and become more complex than ever. In the microbial world, size and complexity are luxuries and mitochondria paid the bill. This new economy of energy eventually led to the appearance of eukaryotic cells. Unlike their simpler cousins, eukaryotes had nuclei compartments to store DNA, protect it, and manage it. They had internal scaffolding organelles and membranes folded in elaborate ways. In short, they were miniature cities compared to the humble huts of bacteria. That shift was monumental. Every animal, plant, fungus, Yumi the cat next door descends from that lineage of eukaryotes. Here's a quirky aside. Scientists sometimes call mitochondria the powerhouses of the cell, but they're more like ancient tenants that never left. If you look at their DNA, it's not human, not animal, it's bacterial. They carry the echoes of their ancient independence inside every cell of your body. You are, in a very literal sense, a chimera, a blend of two lineages stitched together billions of years ago. Of course, biology doesn't move in straight lines. The rise of eukaryotes didn't instantly erase microbes. For over 1 billion years, life remained dominated by the microscopic. Bacteria and archaea continued to thrive, shaping Earth's cycles in ways they still do today. But slowly, in pockets and niches, eukaryotes spread, testing new forms. Some remained single-celled content to float in oceans. Others began tentative experiments with cooperation, sticking together, dividing tasks. These collaborations, humble at first, sowed the seeds of multicellularity. Academic debates heat up here. Did multicellularity evolve once or many times independently? Evidence suggests the latter. Different groups of organisms, plants, animals, fungi, even some algae, all seem to have discovered the trick separately. It's as if multicellularity was an idea too good mod. To repeat a solution life stumbled upon again and again in different corners of the biosphere. Each attempt brought its own strategies, but the principle was the same. Unity is strength. Now imagine what this looked like on Earth. In shallow seas, colonies of single-celled organisms clumped together, forming filaments or spheres. These colonies weren't yet true organisms, but they were steps in that direction. Some cells, specialized maybe one type, stuck to surfaces, while another focused on reproduction. For the first time, life was learning that cooperation could build something greater than the sum of its parts. Meanwhile, oxygen levels didn't just stabilize, they fluctuated wildly. At times, they dipped, plunging Earth into new crises. Around 1.8 billion years ago, oxygen levels may have crashed, plunging the planet into what scientists call the boring billion. The term is misleading, though, because it wasn't boring for life. It was a billion-year-long experiment in resilience. Oceans stratified with oxygen-rich waters near the surface and anoxic sulfidic depths below. Microbes adapted to these shifting zones, building layered ecosystems that foreshadowed future complexity. Here's a humorous aside: if you had a time machine and visited Earth during the boring billion, you'd probably complain. Nothing to see here, just slime and mats. But if you stayed long enough, you'd realize it was anything but boring. Hidden in that quiet era were the seeds of complexity, eukaryotes refining their machinery, oxygen levels, dancing geology, preparing for tectonic dramas to come. Sometimes, history's most important chapters look dull until you know what they're building toward. While life simmered, Earth itself was restless. Supercontinents assembled and broke apart in cycles. Columbia Nuna Rodinia. Mountains rose, weathered, and fed oceans with minerals. Each tectonic shift altered the stage-changing coastlines, climates, and currents. These slow grinding movements set the stage for bursts of biological innovation. When continents clustered, climates grew extreme. When they split, new shallow seas opened, offering fertile grounds for evolution. And then the planet flexed its extremes again. Around 720 million years ago, Earth plunged into another snowball phase, glaciers stretching nearly to the equator. The seas froze, the land disappeared under ice, and life was squeezed into tiny refuges. How did it survive? Probably in cracks in the ice, in hydrothermal vents, in briny pools where freezing was incomplete. It's a reminder that life doesn't need the whole planet, or just a corner, just a niche, just a crack of possibility. When the ice finally retreated, the world was transformed. Glaciers ground mountains into dust, releasing nutrients that fertilize the seas. Oxygen rose again and ecosystems exploded with new possibilities. This post-snowball rebound may have set the stage for one of the most dramatic moments in life's story, the Cambrian explosion, when diversity surged in ways never seen before. But let's not rush too fast. Before animals burst onto the scene, Microbial life continued its quiet rule. Stromatolites still grew. Microbes still cycled carbon, nitrogen, sulfur. Even in this age of oxygen, they were the silent majority, the invisible architects of habitability. The paradox is striking. For all the drama of eukaryotes and multicellularity, microbes never stopped being the backbone of life and still are today. Here's a strange, wonderful side note. Deep inside your own body, in your gut, trillions of microbes still live, echoing that ancient truth. You are not just a descendant of microbes, you are a walking ecosystem of them, carrying a living memory of life's earliest days. So where does this leave us at the end of this chapter? Earth, around 700 million years ago, was no longer just a microbial world. It was a stage brimming with possibility. Oxygen had risen and fallen. Continents had moved and cracked cells had merged and cooperated. The planet had endured catastrophes and come out richer each time. The stage was set, the curtain about to rise on life as we know it. Not invisible anymore, but visible, tangible and astonishing. And here's the poetic thought to close everything that makes us human. The complexity of our cells, the breath in our lungs, the ecosystems we depend on was built on catastrophes, chance and cooperation. Earth wasn't handed life ready-made. It forged it through fire, ice and patience. And as the Proterozoic era waned, the whispers of biology began to crescendo into the first chorus of animals. The Cambrian explosion, it really deserves that word, explosion. For nearly 3 billion years, life had been whispering in microscopic tones, microbes quietly shaping the atmosphere, oceans and crust, with little to show for it on the surface. Then, suddenly, about 541 million years ago, the seas became noisy with invention. It was as if the planet flipped a switch and life went from sketches in the margins to a full-blown gallery exhibit of forms. Let's begin with the backdrop. The world had just emerged from brutal snowball Earth events. Glaciers had scraped continents, bare, grinding mountains into dust that washed into the seas as the ice melted. Those sediments enriched the oceans with nutrients, fueling bursts of productivity. Oxygen levels rose again, crossing thresholds that allowed larger, more active organisms to survive. The stage was set, and evolution was itching to perform. And what a show it was! Imagine diving into a Cambrian reef. Around you scuttle trilobites, armored arthropods with segmented bodies and compound eyes. They move in herds across the seafloor like underwater beetles, sometimes burrowing, sometimes swimming. Above, predators like anomalocaries sweep through up to 3 feet long with spiny appendages reaching forward like alien chopsticks and a circular mouth lined with jagged plates. To us, they look bizarre, but to trilobites, they were terrifying. Predation on this scale was new, and it drove an evolutionary arms race. And arms races mean defenses. Creatures evolved shells, spikes, burrowing habits, even camouflage. The seas became a theater of strategy, offense, defense, adaptation, repeat. It's here that ecosystems grew truly dynamic, not just collections of organisms, but webs of interaction, predator and prey, grazer and filter feeder, scavenger and builder. The Cambrian wasn't just a boom in species, it was a boom in relationships. Here's the quirky fact. Paleontologists have a love-hate relationship with this period. They adore it because the fossils are extraordinary, preserved in places like the Burgess Shale in Canada and Chengjiang in China. Delicate, soft-bodied creatures, worms, jellyfish, even internal organs, fossilized in exquisite detail, giving us an unprecedented window into ancient seas. But they also debate endlessly about the why. Why then, after billions of years of microbial monotony, did life suddenly diversify? Some argue oxygen was the key. Without enough oxygen, large energetic organisms simply can't exist. Others point to genetic innovations, especially the rise of Hox genes, which act like master architects in embryonic development controlling body plans. With Hox genes, evolution could explore new forms more rapidly. Still others credit ecological escalation. Once predators appeared, prey had to respond, and that back and forth fueled diversity. The most likely answer, all of the above. Evolution doesn't work with single levers. It thrives on synergy. Now let's tour the Cambrian cast. Take Hallucigenia, a spindly worm with claw-tipped legs and a row of spikes down its back. When first discovered, scientists reconstructed it upside down, mistaking its spikes for legs. Then there's Opabinia, with 5 eyes and a long, flexible proboscis tipped with a claw so strange that when the fossil was first shown at a scientific meeting, the audience laughed out loud. But strangeness was the rule, not the exception. And yet, within that strangeness were ancestors we'd recognize. Early chordates like Picaya swam with a notochord, a stiffened rod that was the forerunner of the vertebral column. That humble swimmer, no larger than your pinky, represents the lineage that would eventually lead to fish, reptiles, mammals, and humans. To look at it is to glimpse your great-great-great-grandparent a billion times removed. The Cambrian explosion also changed geology. With burrowers churning sediments, oxygen penetrated deeper into the seafloor. Coral-like organisms began to build reefs, providing habitats for countless others. Skeletons altered the chemistry of the oceans, locking calcium and carbonate into structures that reshaped entire ecosystems. Life wasn't just adapting to Earth, it was engineering it. Here's a humorous aside: if natural history documentaries existed back then, David Attenborough might have narrated them in disbelief. Here we see Vivaxia covered in protective scales, slowly crawling along. And here comes Anomalocaris, the ocean's first apex predator, ready to ruin someone's day. It really was planet Earth's pilot season, with experimental species auditioning for roles. Most were cancelled quickly. Indeed, many Cambrian creatures left no descendants. They were evolutionary prototypes, strange attempts that didn't survive the long game. But the survivors carried forward blueprints that still define life today. Arthropods became insects, spiders, crustaceans. Chordates became vertebrates. Mollusks became snails, squids, and clams. The basic architectural plans of life were locked in, still recognizable 500 million years later. Here's another quirky fact. The Cambrian explosion wasn't as sudden as it looks in textbooks. Fossil preservation plays a big role. Once skeletons evolved, fossils became far more common. That doesn't mean life wasn't diversifying before, it just means we can finally see it clearly. The explosion might be partly an artifact of record keeping, though it was still a genuine burst of innovation. Academic debates rage over timing. Some argue the explosion was a true singular event, while others see it as a long fuse lit in the Ediacaran period and sparking gradually. Either way, by the end of the Cambrian, Earth's biosphere had transformed. It wasn't a microbial world anymore. It was a biosphere with teeth, eyes, shells, and speed. Imagine standing on a Cambrian shoreline. The land is still barren rock and sand, maybe a few microbial mats clinging to tide pools. But under the waves, it's chaos in motion. Swarms of trilobites scurry across the seabed. Worms wriggle through sediments. Giant predators dart overhead. Sunlight filters through shallow water, illuminating colors and patterns we can only guess at. It would look alien, but it would also feel oddly familiar, because this is where our kind of life visible mobile complex first took hold. And perhaps the most profound lesson of the Cambrian explosion is this: once complexity emerges, it doesn't go back. Life can collapse, it can suffer extinctions, it can reset, but it never returns to absolute simplicity. The door opened in the Cambrian, and it has never closed. By the end of this period, Earth was no longer experimenting with microbes alone. It was building ecosystems predators prey and relationships that would echo through deep time. The Cambrian explosion wasn't just the dawn of animals. It was the dawn of drama in nature. And from here, the stage would only get more crowded, more dangerous, and more beautiful. By the time the Cambrian explosion tapered into the Ordovician period, the world was unrecognizable compared to its ancient microbial past. The seas weren't just scattered experiments of strange body plans anymore. They were dense, layered ecosystems thrumming with life at every level. The blueprint of modern biology had been written, but evolution was far from finished with its drafts. This next chapter in Earth's history was one of elaboration, expansion, and escalation. If the Cambrian was the spark, the Ordovician and the ages that followed were the wildfire. The Ordovician seas, around 485 to 444 million years ago, were teeming. Trilobites still crawled and swam in abundance, but they now shared their world with brachiopods, mollusks, bryozoans, and early corals that began constructing reefs far larger and more elaborate than anything the Cambrian had produced. Nautiloid cephalopods, the ancestors of squids and octopuses, grew into fearsome predators, some stretching several meters long, jet-propelled rockets of the Paleozoic oceans. To a trilobite, a nautiloid must have seemed like a submarine with teeth. Meanwhile, tiny but crucial innovations continued at the microbial level. Plankton diversified, filling oceans with drifting clouds of productivity. These microscopic organisms formed the foundation of food webs, pumping energy into the system like invisible engines. And for the first time, life began to reach cautiously beyond the water's edge. Early plants, little more than moss-like mats, crept across damp shorelines. They didn't look like much patchy green films on bare rock, but they were rewriting Earth's surface chemistry. By pulling carbon dioxide from the air and stabilizing soils, these pioneering plants were laying the groundwork for forests to come. But before we get too comfortable on land, let's stay in the water a bit longer. Because the Ordovician also saw one of life's earliest great tragedies, a mass extinction. Around 454 million years ago, climate swung violently. Glaciers advanced, sea levels dropped, and shallow marine habitats collapsed. An estimated 85% of species perished, marking the first of Earth's Big Five extinctions. The irony is painful. The same glacial cycles that sculpted new niches also wiped them clean. Yet, once again, life endured, adapted, and rebuilt. Here's a quirky side note if you're ever feeling fragile. Remember that brachiopods survived this extinction and they still exist today. They've been called living fossils, quietly enduring for over 500 million years, even though they never became glamorous like trilobites or dinosaurs. Sometimes, persistence is its own form of victory. Now let's leap forward into the Silurian and Devonian periods, roughly 404 to 359 million years ago. These were ages of innovation that pushed life into entirely new realms. Plants didn't just sprawl on shorelines, they grew taller, sturdier, more vascular. By the Devonian, the first forests appeared, casting shade over rivers and altering the atmosphere. Roots split rock soils, formed, and landscapes shifted. Rivers carried nutrients into seas, fertilizing marine ecosystems further. Earth was becoming greener, literally and figuratively. In the oceans, fish were undergoing their own revolution. Jawless fish, primitive and armored, had dominated earlier seas. But now, jaws appeared, a simple innovation with staggering consequences. Suddenly, vertebrates could bite you and hunt in entirely new ways. Placoderms, armored fish with bony plates, became the apex predators of their time. Imagine a Dunkleosteus, a monstrous placoderm with jaws strong enough to shear through armor, lurking in Devonian waters. If the Cambrian gave us predators like Anomalocaris, the Devonian gave us true jaws of death. And here's where the story takes a thrilling turn. Some fish began to flirt with land. Lobe-finned fishes, with fleshy, muscular fins, adapted to shallow, swampy environments. Over generations, those fins became stronger, more jointed, capable of bearing weight. Lungs, originally simple adaptations for gulping oxygen in stagnant waters, grew more efficient. Step by step, inch by inch, vertebrates tested the boundary between water and air. Eventually, the first tetrapods, the ancestors of amphibians, dragged themselves onto muddy shores. They weren't elegant. They probably looked more like clumsy, gasping salamanders than graceful pioneers. But they were history's first four-legged explorers, the vanguard of a grand terrestrial conquest. Let me drop a humorous aside here. Imagine being the first fish to haul yourself onto land. You flop around awkwardly gasping, and every other fish laughs. But in the long run, your descendants invent dinosaurs, eagles, elephants, and humans. Sometimes looking ridiculous is just the price of being first. While vertebrates stumbled onto land, arthropods were already there. Millipede-like creatures and early arachnids crawled across soils, feeding on decaying plants. Insects soon followed, buzzing into skies for the first time. With plants building habitats and arthropods diversifying, the land was no longer barren rock. It was becoming an ecosystem. The greening of Earth had begun, but the Devonian also delivered another extinction punch. Toward its end, about 375 million years ago, a series of crises, possibly tied to climate shifts, anoxic oceans or asteroid impacts, wiped out many marine groups, including most placoderms. The so-called Age of Fishes ended in devastation, clearing ecological space for new forms to rise. Once again, catastrophe reset the evolutionary clock, but the innovations of jaws, forests, and tetrapods ensured life was now more versatile than ever, and that versatility was about to pay off. Enter the Carboniferous period, 259 to 299 million years ago, a time when Earth became a greenhouse jungle. Vast swampy forests of giant ferns, horsetails, and seed ferns stretched across continents. Oxygen levels soared, reaching higher percentages than at any other time in Earth's history. The air itself was supercharged, and life responded in spectacular fashion. Insects grew to enormous sizes. Dragonflies with wingspans of 2 feet patrolled humid skies, while millipedes, longer than cars, crawled through undergrowth. Amphibians thrived in wetlands, their diversity exploding. And crucially, the first reptiles appeared vertebrates that could lay eggs with protective shells, freeing them from dependence on water for reproduction. This innovation opened the land wide, unlocking deserts, uplands, and every habitat in between. Here's a quirky aside: if you think mosquitoes are bad today, be glad you weren't alive in the Carboniferous. Picture a mosquito-like insect the size of your hand buzzing toward you in a swamp thick with humidity. You wouldn't swat it, you'd run. While forests expanded, something else extraordinary was happening underground. Fallen trees and plant debris accumulated in vast quantities, buried in oxygen-poor swamps where decomposition slowed. Over millions of years, pressure and heat transformed that organic matter into coal. The forests of the Carboniferous gave us the fuel that humans would burn hundreds of millions of years later, reshaping the climate yet again. The irony is staggering. The plants that drew carbon dioxide from the air back then created the coal we release into the atmosphere today. Deep time has a way of looping back. By the close of the Carboniferous, reptiles were poised to dominate. They carried within them the key to conquering land completely: the amniotic egg. This evolutionary innovation was as revolutionary as Jaws' oxygen or multicellularity. With it, vertebrates no longer had to return to water to breed. They could wander far, settle dry uplands, and diversify into new forms. The door to the age of reptiles was about to swing open, and here's where the grand stage of Earth prepared for one of its most iconic performers, the dinosaurs. But before their thunderous steps shook the ground, Earth would endure yet another upheaval: the Permian period, with its towering conifers, sprawling deserts, and the deadliest extinction the world has ever known. So, from the Cambrian explosion through the Ordovician, Silurian, Devonian, and Carboniferous, we've watched life leap from microbes to monsters, from seas to forests, from fragile beginnings to bold expansions. Every step was fragile, every success precarious, every extinction a reset. Yet the story marched on, fueled by chance, catastrophe, and invention. The planet was now bursting with complexity: reefs, forests, insects, fish, amphibians, reptiles. The tapestry was richer than ever, but it was far from finished. The next chapter would bring deserts, dragons, and disaster on a scale life had never faced. The Permian extinction loomed, and only the hardiest survivors would walk into the age of dinosaurs. By the time Earth entered the Permian period, roughly 299 to 252 million years ago, it was already brimming with forests, swamps, rivers, deserts, and oceans, rich with fish, arthropods, and the first reptiles. But now, the planet staged an even greater experiment. It gathered nearly all its land into one colossal continent, Pangaea. Imagine stretching a map until every continent clicked together like puzzle pieces. That was Pangaea, a supercontinent so vast it created deserts in its heart, swamps on its edges, and mountain chains spanning thousands of miles. Life responded with both grandeur and fragility. The Permian was the age of synapsids, reptile-like creatures that were surprisingly our own distant ancestors. Take Dimetrodon, often mistaken for a dinosaur. It wasn't. It lived millions of years before the first dinosaur ever hatched, and it carried a massive sail on its back, possibly for regulating body temperature, possibly for display. These creatures ruled the land long before dinosaurs, prowling deserts and floodplains, hunting amphibians and smaller reptiles. Meanwhile, the seas were filled with brachiopods, ammonites, bony fish, and massive reefs built by sponges and algae. Crinoids waved their feathery arms in gentle currents, while sharks, already ancient by this point, patrolled the waters with quiet menace. On land, forests of conifers, seed ferns and ginkgos grew tall, feeding an array of herbivores. Insects, still giants, thanks to lingering oxygen richness, buzzed through the air. Dragonflies as wide as hawks, beetles the size of rats, scorpions that could reach your knee, all roamed in humid forests. It was a lush, teeming planet, but Pangaea had consequences. Its vast interior was dry, cut off from the moderating effects of oceans. Deserts spread and climates grew extreme. Monsoons lashed coasts, while inland basins baked in seasonal heat and froze in winter. Yet even in these harsh conditions, synapsids thrived, adapting with sturdy bodies, sharp teeth, and increasingly mammal-like traits. For the first time, creatures with warm-blooded tendencies appeared. These proto-mammals were experimenting with metabolic strategies that would one day fuel the rise of fur milk and constant body temperature. Here's a quirky aside: paleontologists sometimes joke that the Permian was like a trial run for mammals. Dimetrodon might look reptilian, but its skull with a single temporal opening places it closer to us than to lizards. In other words, your distant family tree includes sail-backed predators stalking swampy floodplains 270 million years ago. Talk about awkward ancestry photos. But as life flourished, danger brewed. Around 252 million years ago, Earth entered the most catastrophic extinction event in its entire history. The Permian-Triassic extinction, grimly nicknamed the Great Dying. Over 90% of marine species and about 70% of terrestrial vertebrates vanished. Coral reefs collapsed. Trilobites, survivors of every extinction since the Cambrian, finally disappeared forever. Synapsids, once dominant, were nearly wiped out, reduced to a handful of struggling lineages. What caused this apocalypse? Academic debates, rage. The leading suspect is massive volcanic activity in Siberia, the Siberian Traps. For nearly 1 million years, colossal eruptions belched lava, ash, and gases, covering an area larger than modern-day Europe. The atmosphere filled with carbon dioxide, spiking global temperatures by as much as 10 degrees Celsius. Oceans warmed, oxygen dissolved poorly, and vast dead zones spread. Acid rain fell, poisoning soils and waters. Methane may have erupted from ocean floors, amplifying the greenhouse spiral. It was a perfect storm of environmental collapse. Imagine standing on Pangaea as this unfolded. Skies red with volcanic haze, seas bubbling with anoxic tides, forests dying, rivers choked with ash. The ground itself seemed to rebel. Survival wasn't about thriving anymore. It was about enduring chaos. Only the hardiest creatures made it through: small burrowers, adaptable reptiles, resilient plants, and certain opportunistic fishes. The rest became ghosts in stone. Here's a chilling but fascinating side note. Some scientists think the extinction was so severe it nearly sterilized Earth's biosphere. Recovery took millions of years longer than any other mass extinction. For nearly 10 million years, ecosystems remained fragile, dominated by disaster species, small generalist organisms eking out survival in unstable climates. It was like evolution was holding its breath, waiting for conditions to stabilize. But eventually, stability returned. And when it did, Earth was poised for a new cast of characters. The Triassic period dawned with survivors ready to explore niches left empty by catastrophe. Among them were archosaurs, the ancestors of crocodiles, pterosaurs, and dinosaurs. These small, agile reptiles would rise from the ashes of the Great Dying to dominate the next 180 million years. Mammal ancestors lingered too small and furry in the shadows, biding their time. Let's take a humorous pause here. If Earth were a TV series, the Permian finale would have been the darkest season yet. Catastrophic, apocalyptic, almost cancelled. But then came a reboot with a new cast. Enter dinosaurs, striding confidently onto the stage like breakout stars. The ratings were about to soar. Still, we shouldn't rush past the sheer weight of the Permian extinction. It was the single greatest pruning of life's tree, shaping everything that followed. Without it, synapsids might have continued ruling, and dinosaurs may never have emerged. Even mammals, including us, exist partly because others didn't make it. Catastrophe reshuffled evolution's deck, and chance dealt the next hand. By the close of the Permian, Earth had been scarred, but not silenced. The biosphere was thinner, quieter, but full of potential. Seeds of resilience were already sprouting, small reptiles ready to adapt ecosystems, ready to rebuild oceans, waiting to recover. The stage was reset. The spotlight dimmed, but the curtain was about to rise again. From here, the Triassic would deliver the opening act of the Mesozoic, the age of dinosaurs. It would begin modestly, with small archosaurs scurrying across deserts and coasts. But it would crescendo into an empire of giants. Yet in those shadows, the tiny nocturnal mammal ancestors would endure, carrying a quiet secret that even in a world of thunder, lizards, another lineage, was patiently preparing to inherit the night. The Triassic period opened like a fragile dawn after the long night of the Great Dying. Life was sparse, ecosystems fragile, and landscapes harsh. Deserts sprawled across much of Pangaea's interior, rivers cut through dry basins, and coasts shimmered with new beginnings. It was a world rebuilding itself slowly, piecing together the threads of existence after catastrophe had nearly unraveled the weave. Yet in this barren stage, the seeds of Earth's most iconic dynasty began to sprout. The survivors of the extinction, those small opportunistic reptiles, diversified. Among them were the archosaurs, a group that would eventually give rise to crocodiles, flying reptiles, and of course, dinosaurs. At first, they were modest creatures, many no bigger than dogs. They scurried, hunted insects, darted through brush, and filled the gaps left by vanished giants. But evolution had granted them tools, upright postures, efficient lungs, and adaptability. With these traits, they thrived. As the Triassic stretched on, dinosaurs grew bolder. Some evolved into nimble predators, chasing small prey across floodplains. Others expanded into herbivorous forms, feeding on the ferns and conifers that cloaked river valleys. By the end of the period, dinosaurs were no longer minor players. They were establishing themselves as rulers of the land. And once they took hold, they would reign for over 160 million years, shaping Earth's ecosystems with their footsteps. The skies too transformed. Pterosaurs, the first vertebrates to truly fly, spread their leathery wings over Triassic landscapes. Some were small, gliding like bats. Others evolved into giants with wingspans that rivaled modern airplanes. Imagine looking up at dusk and seeing entire flocks of winged reptiles silhouetted against the setting sun. These were not birds yet, but they were rehearsing for the role that birds would one day inherit. Meanwhile, in the oceans, ichthyosaurs and plesiosaurs emerged. Ichthyosaurs, sleek and fish-like, darted through waves like reptilian dolphins. Plesiosaurs with long necks and paddle-like limbs prowled coastal seas. These marine reptiles reclaimed the waters abandoned by trilobites and placoderms, proving that catastrophe could not erase the allure of the ocean's depths. And yet, even as archosaurs and dinosaurs claimed dominance, another story unfolded in the shadows. Small synapsids, the last remnants of the once mighty Permian rulers, evolved into creatures more mammal-like. They shrank in size, sprouted fur, and became nocturnal to avoid dinosaur competition. They nursed their young, maintained warm bodies, and sharpened their senses. They were not glamorous. They were humble survivors, hiding in burrows and forests. But in their quiet persistence lay the future of mammals and eventually us. Here's a quirky aside. Some scientists think early mammals survived precisely because they were unremarkable. While dinosaurs, roared mammals, squeaked, scurried, and endured. Sometimes the key to survival isn't strength or size, but the ability to go unnoticed until the right moment. As the Triassic gave way to the Jurassic, Earth once again shuddered. Another extinction event struck, though not nearly as severe as the Great Dying. This time, many of the early reptilian lineages vanished, clearing the stage for dinosaurs to rise without rivals. When the Jurassic dawned, the age of dinosaurs had truly begun. But as I tell you this, let me remind you of the thread that ties it all together. Water. From the rains that cooled magma oceans, to the storms that filled the first seas, to the rivers that carved valleys for forests, to the swamps that nurtured amphibians. Water has been there quietly orchestrating. Dinosaurs may dominate the imagination, but it was water that gave them rivers to drink, oceans to swim beside, and climates to thrive in. Now slow down for a moment with me. Picture it, a Jurassic landscape, humid and green, with conifer forests stretching to the horizon. A sauropod, the size of a building, bends its neck to sip from a wide river. Overhead, pterosaurs drift like kites in the wind. In the shadows, a tiny mammal sniffs the air, scurrying back into its burrow. Every drop of that river, every molecule of its water, has traveled through time, from interstellar dust meteorites and volcanic outgassing. It connects stars, rocks, oceans, and life in one continuous cycle. And here we are, billions of years later, still drinking from the same cycle. The water in your glass tonight may have once swirled in a Cambrian sea, frozen in a snowball Earth glacier, or trickled down a carboniferous fern. It may have quenched a dinosaur's thirst, or locked inside a mineral deep in Earth's mantle. It is ancient, patient, and eternal. So, as we close this long journey, let me slow the rhythm even further. Imagine lying back now, eyes closed, listening to the quiet hum of your own breath. Feel the weight of history in that breath, the oxygen made by cyanobacteria billions of years ago, the water molecules forged in stars older than the sun. Everything you are is part of that chain stitched together by time and tide. If you've stayed with me this far, thank you. You've walked through fire and ice extinctions and explosions, oceans and deserts, and watched Earth rebuild itself again and again. The story isn't finished. It continues in every drop of rain, every tide, every heartbeat. So let the thought carry you gently now. Water has always been the storyteller, and tonight it whispers you towards sleep. Let oceans fade into waves of dreams, let ancient rains dissolve into quiet, and let stars blink softly above as if keeping watch.